Thank you all for giving me the chance to be here and for you being here. And thanks very much to the organizers for giving me the chance to see this thing, which until now was a mythic institution to me. And so it's great to actually have a chance to be at the Arizona Winter School. But I should say, as an algebraic geometer, I feel like I'm not quite a foreigner here, but maybe it's like maybe someone who's Dutch visiting Germany, and you realize people speak almost the same language in a funny accent, but there are way more of them. So my intent is to somehow bring us fellow Europeans together and to try to get and to try to communicate some problems and some ideas where there's been a lot of traffic between the arithmetic side and the algebraic side and the topological side and the geometric side. And so I want to, for this series, introduce and talk about questions that take us back and forth. And maybe I should say, first of all, I want to make sure I reach this audience. So when I say things without appropriate definitions, and I don't mean to, please stop me. And please, I realize with a big group, it's hard to feel comfortable asking questions. And maybe even if the older people in the room, if you know I'm saying something idiotic, just pretend, just ask me to define what something or other is. Okay, so a central player in this series of lectures is going to be the Grothendieck ring of varieties. And what I'd like to do today is to start by giving you explaining about the ring. It's very quick to define, but then the questions become interesting very quickly. So let me define the Grothendieck ring. And the thing to think about, you've seen very likely Grothendieck groups in an abelian categories, where notions like formal sums of vector spaces, virtual representations, and varieties unfortunately do not form an abelian category. And but this is intended to be a blunt approximation, which is surprisingly useful. So what I want to do is define this. Let me call the ring. I want to fix a field for this discussion. But I want to say in advance that you should pick your favorite field to think about this, but we're going to want to go between fields or compare answers in different fields. So, and so the examples will involve a bunch of different fields and how they interplay with each other. Okay, so Grothendieck defined this ring in the 1960s as follows. So here's we fixed our K, and I'm going to define the ring. This is non-standard notation that I'll call R, for me being maybe French, not Dutch, then I feel like the A for me are always rings. So this way, this is a ring R, and it depends on the field K, and maybe I'll just call it R often. And so additively, I'll tell you what the generators are. It's generated by or maybe I should say, to begin with, that we're going to have, that when I say varieties, I don't over K, just for convenience, because it's really not going to matter. Let me just say that they're, for people who care, they're finite type schemes over our field, which is, of course, also not the right definition, but that's okay. And so additively, they're going to be generated by symbols of the form X, where X is a variety up to isomorphism. And that's the generators of the additive group. And then the relations are that if you have a closed subscheme, a closed or subvariety, if you wish, of X, then and you have the complementary open U, we'll just declare that X is the closed plus the open, which is fairly, so we're doing something fairly violent to the fairly violent to the variety, and then you can and then maybe one thing to just point out is that we really don't care. You can just quickly check that the class of X by taking Z to be the empty set is the well, that's not quite right. But let me say the class of X you can quickly check is the class of the reduction of X. Okay, so we don't really care about non-reduced stuff. So really think varieties. And now I've told you what it is as an additive group. And now let me tell you what it is as what the multiplication structure is. First, get used to where this should go. And so multiplication, well, all I need to do is to tell you how to multiply two of our additive generators. So if x and y are varieties, I'm going to tell you how to multiply those two classes, and I'm just going to define it to be, I guess give it a little time sign there, as just the product is the product over our field. So that's it. That's the definition. And so clearly, this turns R into a commutative ring. And I guess there's this one small issue about how you define commutative ring. But let me say that it's kind of, as by way of example, that the 0 in this ring is going to be clearly the empty set, the class of the empty set, because empty set cross anything is the empty set. And 1 is going to be the class of a point, or spec k. I guess for the Germans, there we go, there's a German word. Whoops, yeah, that's right, great. Since point times anything is anything, and maybe the one example I'll want to do, or maybe one thing I should say is, right, why was I going on about ring? Well, for some people require 1 not to equal 0, but we actually don't know that yet. So let me take my rings to allow 1 to be equal to 0. Okay, so then here's another class which I'm going to call L, which is the class of the affine line. Sure. Yes, that went the wrong way. Thanks. Good. Great. So this is just the class of the affine line. L, I don't know exactly what L is supposed to be standing for. It could be line or Lefschetz or so. But this is sometimes called the Lefschetz motive for reasons I'll sort of say later. And an example of some algebra inside this ring, the class of P2 is, well, it's P2 is an A2 and an A1 and an A0 and a point. So we get something, I guess I don't need to say that. So P2 is that. And maybe the thing to point out is that this is kind of a field-independent statement. There's nothing about K that's relevant here. And just to give you some practice, you can check that in the Zariski, that if you have a Pn bundle over X, then the class of it is going to be the class of Pn times X. This is, maybe to be clear, this is Pn bundle, I mean in the Zariski topology. Great, okay, good. So this blunt thing will untwist any bundle. And so maybe for motivation, one of the central ideas of mathematics is turning general phenomena, nonlinear phenomena, into linear phenomena. So calculus takes things that are not linear and gives us linear things from which we can work things out. Cohomology, I think of as another example that turns things into groups of rings, from which information can be extracted. And this is sort of think of this as a very blunt way of turning information from getting information from the category of varieties into a ring. So let me give you a feel for this by doing an example. And I think I'll do 3 examples that will carry us pretty far. Whoops, and I should always remember this goes here. Great. So okay, so I want to talk about varieties, but for now, just to get used to it, let me just talk about classical. I'm going to put quotes around everything: geometry, topology. So I don't want to be precise about this, but think about nice geometric spaces. And if you want me to start to be precise, you could say, so think about finite CW complexes. So that's a reasonable topological space. And then in this world, this geometric world, the class of the real numbers, well, every real number is either negative or positive or 0. And the positive numbers are basically the same as the negatives, and the positive numbers are basically like all the reals by way of exponentiating. So assuming I'm allowing those maps, and what I'm saying makes sense, then what that means is that the class of the real numbers is a class that's the negatives plus 0 plus the positive. But 0, these guys are just the class of the real numbers, and then this is just 1, and then that means that the class of R is -1. And so the class of R to the K is -1 to the K. And since you can cut up any CW complex into pieces that look like r to the k's, then what this means is that you just cut up into pieces, add up these minus 1 to the k's, and all you get, the only information in this ring is a single integer. It'll send x to the Euler characteristic of x, or maybe correctly, the compactly supported Euler characteristic of x, and that's all that you get out of it. So it sounds like there's really not so much here. You're losing lots of information, maybe just for comparison later. The empty set is 0, of course, but lots of other things are 0, like S1. You can also have things that are different dimensions that are the same, or different numbers of components. So all these things are 0. It's only an integer, that's all that's there. But in fact, I want to say that even this, there's something really serious going on, and that's just because you've forgotten that when you first see Euler characteristic, it's actually quite serious. Maybe the first thing I'll say is that I was lying here a little bit, or not, I wasn't really lying, but at this point we know that x is going to that times a class of 1, but how do you know 1 is not 0? So I'll leave that as a rhetorical question that probably doesn't belong in a gathering like this anyway. But how do we know that 1 is torsion-free? Like a point is torsion-free in this ring. How would you prove that? So making this work involves some understanding of cohomology with compact supports. This is kind of a non-trivial thing. And then maybe I should say that if you want to go to an even younger stage in your life, then a long time ago, presumably you were entranced by Euler's, by the fact that v minus e plus f is 2 minus 2g when you take a map of contractibles on a Riemann surface, and that's contained in here. The fact that it doesn't matter how you cut and paste, you always get the same number, that is the content of the statement that 1 is not equal to 0 in that ring. So this, what I want to do is that you should, this tells you how you should think of the map from the category of varieties, or from varieties, I should say, to the Grothendieck ring. You should think of it as some sort of Euler characteristic. And in fact, tautologically, it's a universal Euler characteristic that behaves well under cut and pasting and products, just by definition. And so it's capturing some cohomology type thing, and that's why sometimes R is sometimes called informally the ring of baby motives, because you have some very small shadow, in some very vague sense. And you should think of it as the kind of some sort of universal Euler characteristic, although maybe I should put with compact supports to make it, yeah? A ring of, baby. So, thanks. Okay, so let's see what we get when we move from into the algebraic category. And the lesson here, we'll get to what I think is like one of the most important facts from 20th century mathematics, which is, so what I want to say to lead into it is that the fact that a geometric object is also algebraic, which lets it be also, for example, arithmetic, means that it has way more structure than it has a right to have. And so before I get there, let me start with something simpler, which is next example. Let's let the field be a finite field, and then I don't know what this ring is, but I do know a ring that it maps to, because given a variety, I can actually map it to the map. I can get an integer by just counting points, and by points I mean rational points. So they're finely many of them, and kind of obviously they play well with the Let me just quickly flash on the alternate alternate screen. The fact that kind of clearly the number of points in X is the number of points in Z plus the number of points in U, and similarly the number of points on a product is the number of points on the the product of the number of points in the two factors. So we get something which is obviously of arithmetic interest, but then you should think of this as being somehow this should be an Euler characteristic. And I guess a reasonable number of you will not be surprised, but if you go back in time, this was, I think, a surprising notion. Okay, so and that means at least we already know that this is not the zero ring, because point counting, you can actually count them, and you can have a point, and they're always positive for an actual variety. Okay, so the next example, a very different field, the complex numbers. Okay, so where do we start? We can't count points because there are, well, there are too many of them. One of the many problems with the complex numbers. But instead, every complex variety is a nice geometric space. And we can just take the compactly supported Euler characteristic of it. So we already get something. We already get one shadow of this ring, which is that it maps to the integers by taking the compactly supported Euler characteristic. So we have so for example, we immediately see that if that class of P2 of CP2, since we're over the complex numbers, the class of CP2, well, that's L squared plus L plus 1. And from that, we just read off that the Euler characteristic is 3. And I should say that for smooth compact things, the compactly supported doesn't matter there. So that's great. But the amazing thing is that from this, because it's algebrogeometric, you can actually read off more. You don't just know that the alternating sums are 3. You can actually read off every single cohomology group. Now again, the same thing that I think Tony had this issue, depending on how you think about things. I may have this backwards. But that means that's 1, and that's 1, and then these are 0. Just by looking at that, there's a recipe, which I'm not going to fully say, but you can sort of guess that this is a 4-dimensional, this is a complex 2-dimensional thing, complex 1-dimensional thing, complex 0-dimensional thing. And so this is a deep, important, amazing fact, and it comes from Deligne's theory of weights, which I think of as being one of the most amazing things ever. But in this case, I think we'll see how to prove this fairly soon. But before I do, let me just point out that if you're not, I have no idea how incredibly number theoretic you are. So if things like homology groups are things that seem in the complex numbers are strange beasts, let me just point out that even H0 is kind of a surprising thing, because it says that you can pick off the number of components of a smooth, this has to be smooth and compact. I'll say complete. For this to work, for this recipe to work, although there are adjustments that you can do that will tell you information without that. But even the number of components, that says that if I take a whole bunch of smooth complex manifold, compact complex manifolds that are algebraic, and I cut them up in an algebraic way, and I rearrange the pieces, and I have another bunch of smooth manifolds, compact manifolds, then the number of components is the same. They may be different, the dimensions may be different, but they're the same. The number of them is the same. And with a little more thought, you can show that the dimension of the biggest one is the same, but the dimension of the second biggest one might be different. So I have no idea how to prove that, how to get at this in any other way. And in particular, it's false once you leave our happy algebraic world, because we've seen the examples in the real world of S1, which has Euler characteristic 0, which is why I don't like S1. So, okay, so even if you're not smooth and compact, you can still make predictions. And I just want to do an example, which is, so maybe I should say over here, this told you exactly what they were. And now I'm going to tell you something which doesn't tell you exactly what they are. If you take C star, well, that's the class of a line, but that's the affine line, take away the origin. And then this will tell me that somehow H0 is 1. It will indicate that H1, well, in this case, it'll tell me. But somehow it indicates, even though it's codimension 2, it's somehow the error is in one direction. Here's codimension 1. And that minus sign has to do with the fact that we shifted an odd number of degrees. And you don't have to remember anything that I'm just saying right now, just the fact that I want to get across the fact that there is information even in the non-smooth and non-compact case. This is mixed Hodge structures are the objects you want to talk about there. Okay, great. And you can get even more information about the cohomology groups. Let me go back to the smooth and complete case. So I can use this word because Tony used this word. But so cohomology groups of complex varieties have additional structures called Hodge structures. And you needn't know what this is, just that they exist with some additional, you need to know basically as much as you needed to see what Tony said. But there's more, this additional information, again, thanks presumably, I think, to Lean, you can read off by looking at equations like this. Okay, so that's the, so in particular, Hodge structures and counting points feel like very different things. But they really are about vector spaces with certain additional structure. And you really should see them. Like there's no, we'll see why soon that you can actually get quite a bit. They really should be seen as very analogous to each other. Okay, so let me tell you how to at least get at this ring. So I want to tell you how to get at it at least in characteristic 0. So I want to tell you, this is, I think it was her PhD thesis. This is Bittner's presentation of the ring in characteristic 0. And so we're going to need to use something like resolution of singularities, which is why we need it. Okay, so one thing we know is, so ring is generated by all varieties additively. But then I might as well let them be affine, and I might as well let them even, well, and smooth, because any variety I can cut up to piece. I could take this big smooth open locus, and I could take that as a piece and cover that by stratify that by affines. So you just take any complicated thing and just break it up into finitely many pieces, each of which is affine and smooth. But if you think a little bit more, then you'll quickly see you can also it's also generated by projective smooth varieties. And then that will take maybe, that's something, that's a worthwhile thing to briefly think through as well. So a plausible exercise for people who are trying to work things out. And then you get a feel for how to just blithely cut and paste things. And now if you have suppose you have a closed embedding of a smooth into a smooth, even a smooth projective into a smooth projective, then you could blow up z inside x. So this is this thing which takes x and it takes z inside it, and you get the blow up of x along z, and it's exactly the same except z is being replaced by a divisor, a codimension 1 locus, which is the exceptional divisor, which is a projective bundle over z. It's a projectivized normal bundle. So that's all you need to know about blowups. And if you so hopefully many of you have seen the existence of them in this much before. But what it means is that the class of the blowup minus the class of the exceptional, that's exactly the class of x minus the class of y of z, because that's kind of the remainder. When you cut out this thing and cut out that thing, you get the same thing. So that's the and so Bittner's theorem is that that's all you need. Those are the additive. Those will generate the additive relations. So theorem, and there are many reasons why this is one reason that's a great theorem is that the proof is extremely short and clever, using one key hard thing, which is that these are all that this is R additively is, you take the smooth projectives modulo the Bittner relation. We call this bit, that one relation, one type of relation. And the proof is really short. It uses but it uses the very hard and very important weak factorization theorem of Abramovich, I'll get the order wrong, Wlodarczyk, and Matsuki, just alphabetize that in your head, and which says that if I have two smooth projective varieties and they're birational, meaning they have dense open sets that are the same, you can get from one to the other by blowing up and blowing down along things that are smooth inside smooth. So essentially, you only need this kind of surgery to go from one to another. But we only know it in characteristic 0, which is why I'm only saying this in characteristic 0. So maybe if you want to disprove resolution of singularities in positive characteristic, you can try to contradict what's coming. Yep, question up there? I would have to think, because they have to, their approach kind of matches with one approach of doing resolution of singularities. So it would depend on how you proved it in positive characteristic. So in fact, yeah, this is not, I don't think that resolution of singularities implies, like, by itself, that implies the result of Abramovich et al. Yes, so additively it is, and I'll leave, and that's a good exercise that if, for tonight, that if you can't answer, I can tell you the answer later tonight or tomorrow. Yeah, so these are all the generators. These are all you need. Oh, okay, so let me give you some applications, and maybe so basically what I want to say is that we can now get lots of motivic measures. We can get a lot of these Euler characteristic kind of things, because all I have to do is tell you something, define something for a smooth projective variety. Sorry, that one. For a smooth projective variety, and verify that this relation always holds. And if so, then I've won. Then it extends to the entire ring. Oh, it should be able under product too. I forgot that, but that's okay too. So, so maybe here's a good motivic measure. Let me define A naught to be from the varieties to Z, or even better from the ring to Z, the growing ring to Z, which is going to be the virtual number of components. What I mean, it's going to be the number of components for something that's only smooth and projective at various dimensions. So if it's smooth and projective, just count the number of components. And I should say that plays well here because, well, let me just do the special case where X is, well, you can quickly check that the number of components, that's preserved by this. And I'll let you worry about annoying special cases, but if X is irreducible and Z is smaller dimensional and irreducible, then that's 1, 1, 1, 1. And that is a true equation. And so that means that we've just proved that fact I told you earlier, that if you have a finite number of smooth projective varieties and you cut and paste them, you're going to get the same number of, they may be different smooth projectives, but you're going to get the same number of them. So that is the next. So then once you have that, you can jazz that up a little bit more. So for example, you could have the motivic measure that's going to be this for, thanks, I can already guess what. Is that it? For smooth projectives. And see what you get. That generalizes the previous one. And that's something worth thinking through. That's in the notes, but also with an exercise. And I should say, if you know a little bit about the properties of Hodge structures, then you can also prove that Hodge structures are preserved. And let me briefly put this back here, because somehow what matters is that there's nothing exciting that happens Hodge theoretically between these two. That's basically between these two, between the exceptional divisor and Z. But let me not say much about that. But let me tell you a very weird fact, which I'll call Bittner duality. Okay, so I want to take the ring L, R, and I want to invert L. So I'm just adding 1 over L, or I'm localizing. So in particular, well, I'll talk about this ring in a second, in the sense that this is one of many reasons nature is telling us to invert L. That we want this, the ring itself is not right. You want to also invert the line. It's like in topology, the homotopy axiom. You want that to be, you want that to be true. And then here's an amazing involution of this ring where I'm going to send X to X times X divided. Let me do it this way. X divided by that many L's. And this is when it's smooth projectives. But that means that I've defined it for everything. And I should say this works well for products chiefly. Is that clear what I'm saying here? Okay, I think there's scribbles, but hopefully you can see what I mean. So the remarkable thing is the duality, and I'm going to prove it. And but I want to just do some examples so you can see what it does. So it sends a point to a point, obviously, because points are dimension 0. It sends P1 to, well, that's 1 plus L. And so that maps to 1 plus 1 over L, because we divide by L. But what does that mean? It sends A1, which is P1 minus a point, to, it sends A1, which is L, to 1 over L. Did I mess that up? No, that's right. Good. So L goes to 1 over L. So it's not L divided by L to that dimension. It's something kind of different. And I should say that this really is a duality, as we'll check, because it does, you do it twice, you get back to where you start. But even as a duality, I guess all dualities are Serre duality, Grothendieck duality, Poincaré duality. It's always the same thing. And this really is what really is true. And here's how you should sort of see that, which is one of these you should see as being cohomology, which I maybe think of this as H0 and H2, and one of them is being homology. And I'll be vague about that since it's only a vague statement. And maybe the last thing I'll say before, well, actually, let me mention one thing about inverting L. So what's so bad? Nature is telling us to invert L. And the only problem with inverting L is that, oh yeah, sure, yes, please. Because I was literally just subtracting this minus this. So I have to describe L as a difference of, or did I screw? Go ahead. I think that's okay. Can I say more or? Yeah, I think it is worth. It's a surprising. I mean, in any given case you can do it, but it does unexpected. It is kind of a slightly weird thing. Right. So if you want to see where anything goes to, it kind of has to go to. Yeah, you have to write it as a sum of smooth projectives, and then work it out. And very happily, thanks to Bittner's theorem, it doesn't matter how you do it. You're always going to get the same answer. Okay, so we have R. So now I want to mention what goes wrong, what might go wrong when you invert L. So when you localize, this isn't necessarily an injection. So this is only you're going to lose information if this is injection if L is not a zero divisor. Otherwise, you're going to lose information. So a long-standing question, and I guess maybe in this area, the phrase question, conjecture, and speculation kind of means the same thing. So you might hope that maybe L is not a zero divisor. And what's going to come up later is I'll mention that this is in fact false and for really, really interesting reasons. And there are two papers in the archive. The one I'd refer you to is very recent. There's even an update yesterday by Lev Borisov, and the reference is in the notes as well. But the way in which he constructs the counterexample and proves it uses mirror symmetry. So there's something interesting. There's something extremely interesting going. I mean, this is somehow all sorts of fantastic geometry comes up in things like this. Okay, so that's the. So let me just. I feel like I should actually prove things. Maybe I shouldn't, and I'll eat my words. But let me actually try to prove Bittner duality, just to show you how simple. Essentially, everything we do in the ring either is as straightforward as this, or requires insane cleverness, or we have no clue. And this is in the. So here's the proof of Bittner duality. So if it's true, it's got to be true for easy reasons. So we know for sure that the exceptional divisor is a projective bundle over the thing you blew up. And that's the C, let's say, is the codimension. And maybe I will briefly go back and put the picture up because, well, maybe I will not because I will not be able to find it. I'll put the baby picture up maybe. That was the better. Okay, so the exceptional divisor, what you've done is you cut out Z and you replace it by a projective bundle over Z. But the exceptional divisor is projective space times Z, but that is just well, you know what that is. That's that's a bunch of sums of powers of L. Let me multiply both sides by L minus 1. And that turns this, which is the sum of L's, into L to the C minus 1. Good, okay. But now I want to remember Bittner duality, Bittner's relation. It says that let me see if I can I won't bother finding that again. If you add Bittner's relation, let me just write down the next line. You get that the blow-up, so the blow-up of x plus the exceptional divisor of x is equal to, let me do it this way, minus the exceptional divisor of x is equal to x minus z. That was her relation, which we know is true. But now we want to add this and this. And what happens? Well, this L turns up. And this, sorry, this is a minus there. I'm going to subtract. And this L to the C turns up, if I subtract what was here a second ago from that. And now I just divide by L to the dim x. And what I get? Well, yeah, let me just do it this way. And that's that's the dimension of the exceptional divisor. That's the dimension of z. So that's it. That means if we had something, that means that once you apply this Bittner duality thing, it continues to satisfy the same relation. And the same thing works with products too, which I'll let you worry about since that's fairly cheap. So we get this. So there we go. We have something like Poincare duality, which kind of is really somehow easy to prove, although what it tells you is a bit more maybe mysterious. Okay, so let me give you some applications. So recall. So I want to say that you may know what it means for two varieties to be birational, which just means that they have irreducible varieties are birational. If they have dense open sets of each that are isomorphic or that are the same function field. I now want to define stably birational, which basically just means that x and y are stably birational. You're now allowed to add some lines to each side, add some affine spaces. So all rational things are stably rational, birational to a point. And so this is because even taking account the difference in dimensions, this is a strictly weaker equivalence than birationality. And maybe as an aside, there's this rather amazing result of Beauville. Well, let me just say it in words because they're going to be 4 names and look like 6 of Beauville, Collier-Tellen, Sansouk, and Swinert and Dyer, where they give provably an example of something which is stably rational but not rational. So it's something which is a variety which is not rational, and you have to prove that, and that's always hard. And when you multiply it by some affine spaces, it turns into something rational. So how would you, I mean, what amazes me is how you get a hold on that. That's every part of making that work requires something ingenious. Okay, so that's, so these stable birational classes though, let me go back to this. These stable so varieties, irreducible varieties up to stable birationality. Pretend this blob wasn't there, and that's mod. Up to stable birationality, this thing forms a commutative semigroup. Let me call this, because you can multiply two varieties together. So I guess the main thing is that you can write anything. Well, no, there's very little content. That's just a definition, almost. So, but now let me tell you a theorem, which the great thing is I can also, I'll try to have only theorems with one-line proofs. But this is a great theorem because it's so useful. This is by Larson and Luntz, who are others who, Michael Larson, Valerie Luntz, who have had a succession of ingenious ideas on this, which is they said there exists a unique ring homomorphism from our Grothendieck ring to this ring, where you basically send x to x for smooth projectives. That's it. That's the that there is one and only one, and that's going to be and so let me prove it. The proof is as follows. Well, clearly there's a most one because any map is determined by what it does on smooth projectives. So we just have to show that there is one. Well, to show there is one, we just have to show that it respects Bittner's relation. And what is Bittner's relation? I should have this maybe tattooed somewhere on my chest because it keeps disappearing. But so I will do it yet again. It's the fact that the blow up minus the exceptional divisor is equal to the original space minus the thing you're blowing up. And just let's assume everything's irreducible. You only need to check if they're irreducible and irreducible. But then these guys are birational. These guys are stably birational. He's a projective bundle over him. So that's it. That's an equality. So that's the proof. And then less easy is that they will even tell you what the kernel of the map is. The kernel, so notice that L goes to 0. Yes, L goes to 0. You can quickly work out from the case of P1, and P1 is stably birational to a point. And from that, you can work out that L goes to 0. And so any multiple of L goes to 0. And they show that this is the kernel. So anything that goes to 0 in this thing, which you could maybe get a better handle on, must be a multiple of L. Oh, mm-hmm. It's just take all stably birational varieties up to isomorphism. So those are the generators and you of the semigroup. And you know how to add them, just add them formally. And you multiply them by multiplying by multiplying them. And then I guess there are various things to check that if you have if the product of these two, if this is stably birational to this and this is stably birational to this, then their product is stably birational to this product. Okay. Other questions that are around this? Okay, so let me now get to what I want to do with this. So we have this thing which is a great, very general thing, which fairly soon we'll see kind of connects geometry, well, maybe not quite connects, but is a rickety bridge joining geometry and arithmetic. So let me introduce one of the central players in what we're going to talk about, which is called the motivic zeta function. And this is something which should have been defined in the early 1960s, or actually probably even before the early, sometime soon after the Weil conjectures. I'm going to try to convince you, but it was first actually, to my knowledge, written down by Kapranov in 2000, not even in a paper. It's an unpublished preprint, which has never appeared. But the definition is very short. So the motivic zeta function of x, which I'm going to denote like this, it's a power series which is going to live inside, whose coefficients are going to lie inside this Grothendieck ring. And all it is the generating function for the symmetric powers of x. You just take x, you take its symmetric powers, which is also a variety, and just do that. Well, why would you do that? Let me try to motivate it and try to convince you, and by trying to convince you about how well motivated this actually really is. So there's the definition. I feel like there's nothing to say about the definition other than, I mean, there it is. It's maybe if you want to say something interesting, you can vaguely think about it this as being like e to the x, because well, I won't even say why, but it's and also that makes no sense. So first I want to note that if x is an open union of closed, so I'll use u and z for that, then I want to point out that zx of t is the product of the two other motivic zeta functions. Why is that? Well, it's basically because well, let me say the key idea. If I have n points on x, then I've got some number of points on u and some number of points on z, and they can be split up in any possible way. And if you say what that means in terms of the generating functions, that just gives you this here. So, but because this is true, it means that we can really define this on the Grothendieck ring. This plays well in the Grothendieck ring. So we can have zr of t, as a group at least. We can define this by simply, for any element of the ring, just to break it up into varieties and cut and paste and just use what you would have. And it's just a fine definition. So let's get a feel for this. And I'm again going to go through the three examples we discussed. First, there's the topologist example. So let's, example let's say, yeah, the things in quotes. So finite CW complexes, say. Okay, so in that case, I want to point out that in this case, we know that the Grothendieck ring is really boring. It's just the Euler characteristic. There's only a z. So it feels like there's nothing going on. And just to get a feel for sim n, we know that for what the zeta function is, let me do zeta function of a point. Okay, so sim 0 of a point, sim 0 is 1. I should have said that to begin with by convention. And then sim 1, that's 1 point. Okay, that's just nothing to say there. And sim 2 means I need 2 points. 2 points in that point. Well, there's only one way to pick 2 points in that point. And so we just get something real. That's as an example of what you get. This nice rational function. Okay, so that seems stupid, but something is going to happen. So there's this great theorem of McDonald. This is the McDonald of Etienne McDonald. So this is 1962, which says the following thing, which is that he proved that the Euler characteristic of the symmetric powers of x is just 1 over 1 minus t to the Euler characteristic of x. I'm not sure if he said it exactly this way. For example, he might have done it for the case where x is smooth and compact. In that case, you can basically just get rid of these c's for reasons of duality. But this is kind of a strong statement that it tells you about the Euler characteristics of all symmetric powers very quickly, as they're all binomial coefficients in terms of the original Euler characteristic and the symmetric power you have. So it's a great theorem, but what's even better is it has a one-line proof. And the one-line proof is this, which is we know that zx of a point is 1 over 1 minus t. Question? Zx, yes, z point of t, thank you. is 1 over 1 minus t. But we also know that we have this, maybe I should have said this more clearly back here, or further back, that we always have a map, an additive map as groups from R to power series in R, because where you take something and take its zeta function. That's, oh yes, multiplicative and unit group, right. So this is multiplicative, and this is additive. And this is something like an exponential map, which is why I said x goes to e to the x, is a reasonable thing to say. And it's a unit, I mean, it's one, I should say, I'll say that. It's really 1 plus ... The constant term is always 1. Okay, good. So, but what does that mean? Well, I already know that z of x, that x in this group is just the Euler characteristic times of x times the class of a point. So there we go. But the fact that it turns addition into multiplication immediately gives, well, why am I writing it again? Yeah, that's the theorem. There it is. And that's the proof. So you have a slick, so this, even in topology land, this is this is telling you something really interesting. Okay, so that's, so now let me go to the next example. Oh, actually, I am nearing the break in my talk, and I'll resume tomorrow. But let me first say where we're going and give you something to think about for tomorrow, which is the next thing we would think. The next example is when we have a finite field, and in this case, we have a motivic zeta function. And then when we hit it, the motivic zeta function turns into some power series with integer coefficients, because that's what this point counting thing does. And I should say, you know this well. Lots and lots of you know this power series. My question is, what power series is that? And I'll tell you at the start of next day. Great. Okay. Thanks. And we'll continue next day.